Good afternoon, everyone. I'm Carol Feltus, the University Librarian here in Markus Library. We welcome you this afternoon to the second author book talk of our 2018 academic year. I don't really think I need to do a lot of introduction. Everybody knows our guest today. Scientist, physician, author, documentary specialist maker, and many of you are already acquainted with him and our friends in the audience. So without a lot of ado, I just simply want to turn it over to Dr. Siddhartha Mukherjee, and we'll have a great time with him, I'm sure. At the end of his talk, we do have some books available for $10 over at the end of the service desk if you want to pick up one of his books. And please, if you have questions, wait for me to bring you the microphone so that you can be captured on the video. Thank you. Dr. Mukherjee.
Thanks a lot. So just so that I can be heard in the back, I'm going to sit like this. But if I get uncomfortable, I might switch places or something because I'm sitting on the chair edge. But otherwise, no one's going to be able to see me in the back. Can I be heard in the back? Yes. And seen? Yes. OK. All right. Thank you. I'm an enormous fan of the Rockefeller and really the tri-institutional system. My students have subsequently come here as postdocs, and we've collaborated extensively with both Memorial and with Cornell, and to some extent with the Rockefeller. So thank you for all the resources that you've given, at least me personally, in my own scientific and medical life. For me, book talks, especially for this audience, are complicated because it's not clear which direction to move in, because this obviously is an extraordinarily sophisticated audience in terms of your knowledge and understanding of both the history and the context of the science and the medicine. So I thought I'd give you some sort of broad reflections about things I'm thinking about, and then go into the books to pull out the sections. And we try to leave more time at the end for a sort of broader conversation. We can make it quite informal. I will read a little bit, but I don't want to read a lot because then you get too much reading and not enough talking, and it becomes more formal than I want. But I thought for some time about what kind of framework I bring to the writing that I'm doing, and on a very superficial level, the framework is clear. It's I'm writing about newest ideas in medicine, sometimes newest ideas in science. I try to keep a very human focus. And the question then becomes, well, is there something beyond what is happening in the medical and scientific world that's exciting to me? And it was very clear to me that, in fact, there's some thematic elements that run through what I've been thinking about, and I hope, and it's clearer and clearer to me that the writing that I'm doing, either the books or the pieces in the New Yorker or the Times Magazine, are just coming out of those rather fundamental ideas. And so I just put them down as a suggestion, but and I'll try to illustrate them as I move along. A lot of what I've been thinking about and writing about really emerged from the last section of The Emperor of All Maladies. And the last section, again, remember, these are books that I've grown up with. I trained as a fellow and became a cancer physician as I wrote the first book. And there was a moment in which, at the end of the 1990s and the early 2000s, for instance, before we understood much about the immune system and cancer and microenvironments, there was a moment in which there was an exhilaration that we would find the genes that had been turned on or turned off, oncogenes and tumor suppressor genes, in cancer, and by delivering pharmacological therapy against these gene products, we would solve cancer, create a new kind of way of thinking about cancer. That exhilaration, I tried to capture that exhilaration in the Emperor Maladies. It was a very important time for us as writers and thinkers. And that exhilaration was sort of this kind of idea. You find a target, you inhibit the target. Sometimes you might have to activate the target, and you'd kill your cell, your virus, your bacterium. And that was drawn, of course, from a very classical model. If you could find an antibiotic, you would direct that against a bacterium. And somehow we felt then that this model would translate rather easily into complex diseases like cancer, and perhaps diseases beyond cancer, medicine beyond cancer. And this is based on the work of foundational work of many people, including work by Paul Ehrlich and others. The idea of specific affinity, the phrase, so much of science is about language. The phrase "magic bullet," which came out of his own coining. And then actually, this is a nice picture of how Ehrlich imagined not just the use of antibiotics, not just the use of antibodies, but the use of human therapeutics in general. Over here, he imagined that malignant cells would present a whole series of targets here, shown as various blobs in various shapes, and small molecules, medicines, antibiotics, antibodies would bind to these, inhibit them, and you would somehow kill the cell or activate something, and you would therefore get cures for all sorts of diseases. And in fact, of course, in his own lifetime, he'd been very influenced by what he himself and others had done with antibiotics, antituberculotics, and other kinds of ways of staining cells. But then that exhilaration, as many of you know in the field, began to dim. Not completely. There were striking successes. Gleevec is a striking success. Imatinib is a striking success. But the idea that you could do this across all cancers began to dim, and we began to have internal challenges within our own field to rethink how to have a kind of framework of thinking about medicine. And whether the potently reductionist models that we had brought to human therapeutics may need to be questioned, whether we had been over ambitious and perhaps deluded ourselves in being so powerfully reductionist about human therapeutics, and whether we should think again somehow from scratch. So that motivated a lot of my work. It motivated the documentary that I did with Ken Burns. The last section of the documentary talks about some of the disappointments, some personal disappointments that I felt in growing through this field. And what might one do next? Well, one thing you could say is a pox upon all of that, which would come to no good, because after all, the animus to cure diseases is important. But the other way to think about it is to perhaps think of different models, to think of different ways of thinking about how we might reorganize our ways of thinking about human medicine and human therapeutics. So if I took back and took a step back and asked the question, what happened after I finished the first book and went into my documentary, for me, it was a lot about building up a whole sense of how to organize my thinking around medicine. And so, again, just to go back to the original idea, find target, inhibit, rarely activate target, and kill a cell, I began to try to think about, I'm not the only person, but a field began to try to think about reorganizing our understanding of human physiology based on what I might say building upwards rather than building downwards, from gene to cell to organ or environment. And this sounds like a very abstract concept, but in fact, it actuated a massive change in my own laboratory. I can talk about that. I essentially erased much of the work that we had done before and began to concentrate on completely different kinds of problems, because I felt that we had reached a place where you could publish papers, but the human impact of those papers would be very limited. I felt very empty, personally very empty about it. And so I changed my laboratory completely. I stopped projects, and I can talk more about that at some point of time. I stopped projects, completely switched around things, and started doing new things. I'll talk a little bit about what those are. But the idea here was that to rethink pathology, perhaps, moving upwards, with an especial interface or interest in what I might call this edge of pathology, the cell, organ, environment edge of pathology. Why do cancers metastasize only to some locations and not to others? What is it about the soil that makes the seed flourish? An idea that has a long history but had somewhat been neglected in cancer. What is the role of cellular therapies? Rather than focusing our attention on BCR-ABL, should we be transplanting cells that can kill cancer cells? This grew, of course, out of an interest in immunology. And again, to some extent, going right down to not just genes, but complex networks of genes and how they might create various ways of thinking about diseases. So I'll read a little bit. Let me see if this next. I'll read a little bit from this new work that I've been doing and talk a little bit about that, but really focusing on these areas. And one idea that I was very intrigued by was, the two ideas I was very intrigued by. One was seed and soil. So I'll read something from a big piece that I wrote on seed and soil. The second idea I was very interested in is the idea of homeostasis. So how is it that organisms have mechanisms to self-regulate, how these networks can in fact self-regulate, but also can, because they are not so obvious to human understanding, can defy very powerful reductionist attempts to try to direct therapies against them, and why we can be fooled and deluded if we want to simplify things, remembering all the time that there had been some signal successes, at least in cancer, when we had used this kind of very top-down model of finding targets and therapies. So here's a piece that I wrote for The New Yorker, very much inspired by these ideas. This happened while I was changing the laboratory that I was writing new grants and trying to figure out why the hell I was doing the things I was doing. So this is a section. Cancers, like mussels, mussels, proliferate in congenial habitats, and like mussels and sea creatures, they can create environments that help them resist predators. Seed therapies kill cells, but that's something like spraying a lake with a mussel poison. Soil therapies, by contrast, might change the habitat. When I asked one of the scientists about a kind of clinical study that excited him because of its therapeutic potential, he discussed an unusual study in which patients who are diagnosed with a primary melanoma, such as his own father, will donate blood so that researchers can identify their genetic markers and their immune cell composition. By studying how they fare over time, he said, we might learn which patient populations are particularly susceptible and which are particularly resistant to cancer. Cancer is no more a disease of cells than a traffic jam is a disease of cars. The British physician and cancer researcher D.W. Smithers wrote in The Lancet in 1962. A traffic jam is due to a failure of the normal relationship between driven cars and their environment, and can occur whether they themselves are running normally or not. Smithers had overstepped in his provocation. The uproar that ensued, and I'd encourage people to read the letters that came out of Smithers' talk. The uproar that ensued was clamorous and immediate. Smithers complained that he had been lacerated by Occam's razor. By arguing that cellular relationships were responsible for cancer's behavior, he had committed the cardinal sin of multiplying the factors that oncologists and cancer researchers had to consider. To deny the importance of cells in tumor growth would be like denying the importance of people in sociology, he later clarified. Cancer cells were, of course, a necessary condition for the disease. But he went on to say they were not a sufficient one. His real aim was to get beyond oncology's obsession with its internal combustion engine, the cellular automaton and its genes. And it's only after his death that the field began to come to grips with that message. You write, so this is a page break here. By the way, so this, when I write a piece for the New Yorker, we actually have invented a kind of peer review process. We send it out to about 100 readers beforehand, and they make comments. We don't take all the comments. We incorporate some of the comments and so forth. What's interesting is when this was sent out, still in 2017, the Smithers comments generated an enormous storm of commentary back. Many people said they said it's still nonsense, and they may be right. But what's interesting about it is that this idea that cancer is not going to be solved, and in fact, not even the disease can't be fully explained by a kind of monomaniacal concentration on the cell alone, without consideration of its environment, its immune environment, its microenvironment, its metabolic environment, its endothelial environment, still in 2018 generated an incredible provocation. I found that very interesting. You ride the subway one morning, the train is delayed at 59th Street, and a man in a Yankees cap sneezes on you. At work later that week, you feel the chill entering you quietly. You take a cab home, now sniffling, cursing the sea line, and retracing your steps. There was the culprit with the cap, the empty seat that that should have raised suspicion, and that slightly moist steel bar that you should never have touched. What you don't think about are the 6 other passengers sitting nearby who also got sneezed on, but none of them are sick. This is medicine's denominator problem. The numerator is you, the person who gets ill. The denominator is everyone at risk, including all the other passengers who were exposed. Numerators are easy to study, but denominators are hard. Numerators come to the doctor's office, congested and miserable. They get blood tests and prescriptions. Denominators go home from the subway station, heat up dinner, and watch the strain. The numerator persists, and the denominator vanishes. But why didn't the denominators get sick? The pathogen exposure was the same, but the hosts were different. And yet, even the term pathogen is misleading. A pathogen is defined by its ability, to be pathogenic. But that may not be an inherent attribute. It may be a relationship, an interaction with the host. And that returns us to the problem of the early detection paradigm. Suppose we could install tiny sensors in people which would regularly scan their blood to find circulating tumor cells, conducting an ongoing liquid biopsy. We'd be catching cancers earlier than before, but as with the doctors in Seoul, refers to some other part of the article, we might end up over-treating more cancers than ever before. That's because these circulating tumor cells might augur metastatic cancer in some patients, while in others, the Mets never seem to take hold. Why didn't the Mets take hold? The old answer was the cancer wasn't the right kind of guest. The new question is, should we be looking for the right kind of host? I talked to Anthony Ricciardi, who's a professor of invasion ecology at McGill University in Montreal. Ricciardi, a biologist, grew up on the banks of Lake St. Louis, which bulges out from the St. Lawrence River, the route through which the mussels had metastasized into the Great Lakes. I asked him why those freshwater mussels went into hyperdrive when they came to our lakes, and the background to this is that they weren't actually the mussels. The same mussels are a non-invasive species in their native lake. So if you take this, it's the same. The essay begins with the question: if you think about cancer in an autonomous manner, if you think about mussels in an autonomous manner, it turns out that some of them are actually natural residents in their own native lakes, but they're non-invasive there. If you take that same mussel and you transplant it into a different lake, it becomes extraordinarily invasive, and that's the basis of the. So anyway, I asked him why those freshwater mussels went into hyperdrive when they came to our lakes. You've got to understand the dynamics of invasion ecology, he said. It's a series of dice rolls. Most organisms introduced into a new environment will fail, often because they arrive in the wrong place at the wrong time. Vast numbers will die. Piranhas were dumped into the lake for years from aquariums, but they can't establish because the temperature isn't right for them. But overall, would you say the temperature of the water was the key, I asked? The water temperature is a factor. The water chemistry could also have contributed. So it's a combination of temperature and the salinity. No, but also the calcium content. That's absolutely important. I added that to my list of drivers. Temperature, salinity, calcium, and the fact that there weren't any well-adapted predators. The native fish in these lakes won't touch the mussels. Neither will most ducks. Ducks? He sighed, as if tasked with explaining an immensely complex theorem to a child. There are many contributing factors, although some of these factors are clearly more important than others. It's all context dependent. And so it went. For a cancer geneticist like me, it was an exercise in frustration. Every time I tried to pin down a principal cause for the invasion of mussels, I was presented with another contender. Disheartened, I gave up. Perhaps we all gave up. Considering the limitations of our knowledge, methods, and resources, our field may have had no choice but to submit to the lacerations of Occam's razor, at least for a while. It was only natural that many cancer biologists, confronting the sheer complexity of the whole organism, trained their attention exclusively on our pathogen, the cancer cell. Investigating metastases seems more straightforward than investigating non-metastases. It's tough to study those who haven't fallen ill. So that's, again, this idea from, this piece is called Invasion Equation. It came out in the New Yorker. Generated lots and lots of controversy. So just keeping going along. Obviously, one feature of this, what I've been thinking about is, just keeping cognizance of time. We're good. One feature I've been thinking about, again, is to organize my thinking along lines of these, but keeping a strong focus on human therapeutics and really distancing myself to some extent from projects that don't have one immediate step into human therapeutics, which has obviously some costs associated with grant funding, for instance. The three areas, again, that I was interested in, as I said, are genes and genomes, but not genes and genomes as simple targets, but as maintainers in network-like phenomena of the stability of an organism. I was personally very excited by new work coming out of many laboratories, including Jonathan Pritchard's laboratory. Some of you may have known this, which showed that, in fact, small variations, I'm going to abstract this somewhat from what was published, but small genetic variations in genes that might seem to lie in pathways that we have defined, in fact, have incredible pleiotropic effects on cellular physiology. So much so that they defy our capacity to line them up in simple organizational systems. Now, that itself is a provocation. I think one of our jobs is to draw line diagrams in which we say, this signal goes downstream to that signal, goes then to that signal, and thereby generates this process. One of the things that Pritchard has found is that, in fact, if you look at disease physiology, and others have found, actually, we have found, if you look at disease physiology, you can often track back disease physiology using genetic screens to things that track far outside what you might expect as disease networks. We throw all of those away. Those are the denominators. We throw all of this away. We concentrate our attention on things that are sensical to us. But of course, as many of you who've actually done these experiments know, that a vast majority are thrown away. The 3 or 4 that make sense to you are kept most of the time, not all of the time. So I'll read now, again, so this is the same idea. I'll read now, I just don't know what the next slide is. I can skip that. I'll read now a little bit from this idea of genes and genomes, and then move on to some things about cells. Actually, no, I was going to say, I'll read now from Genes and Genomes, but before that, I wanted to read another piece which just came out, which is a very tough piece to write for me for lots of reasons, technical reasons, on my father's death. Have people read that? It came out in the New Yorker 2 weeks ago. But this piece is about the idea of homeostasis and the fact that we imagine or create very linear systems of medical thinking. But in fact, these linear systems of medical thinking are often defied, not because they're out to make us foolish, but because that is the nature of biology, because the nature of biology, the nature of physiology is to counteract constantly, often, perturbations from the environment. And our interventions, whether they be medical, are exactly that, are perturbations of someone's decaying or maintained physiology. For me as a son, tending to my father's death, that was the message. The message was that everything that I ended up doing as a physician, tending to my own father, tended to go wrong. And at some point of time, I said, either I'm a terrible doctor, which may also be true, but also it's possible that everything that we're doing is a perturbation. So why not then say the entirety of medicine is a perturbation of an organism whose natural direction, once they have a pathology, is moving in one way. They're moving southwards, as it were. So therefore, every perturbation that we're doing is only going to be resisted and actually be counterfoiled by what's happening to the natural physiology. This is not meant to be defeatist. It is only meant to remind us that if we think about these medical perturbations, if we think about medicine, human medicines, we have to be a little wiser than I think we've been in the past about how to really get them to take root in the soils that, obviously, in the soils that are not working. So this is a section, again, from this second piece. This is called My Father's Body at Rest and in Motion, obviously referring to Newton's laws. And the central sort of conceit of this piece, to some extent, is to contrast the kind of thinking that we inherit from physics, Newtonian thinking, and try to say, well, what does it make sense in medicine? Does it make sense in biology? Does it make sense in cancer medicine? So it picks up in the middle from this idea of homeostasis. In the late 1920s, the physiologist Walter Cannon coined the term homeostasis, joining together the Greek homeos and stasis, stillness. Homeos is similar and stasis, stillness. The capacity to sustain internal constancy was an essential feature of an organism, he argued. His work was rooted in his experiences working with Allied troops during the First World War as he studied the physiological complications of traumatic shock. But it was also inspired by the work of predecessors, such as the 19th century physiologist Claude Bernard, who wrote famously, "The constancy of the interior environment is a condition of free and independent life." What is true of a well-functioning institution may also be true of the bodies that staff it. Consider temperature. The normal human body maintains an extraordinarily narrow range, somewhere between 97 and 99 degrees, despite enormous and often unpredictable variations in the environment. I boarded my Air India flight on a chilly autumn day in New York and was hurtled in an aluminum tube into unseasonably warm Delhi. But my core temperature, had I measured it, would have changed not 1 degree. And emperor penguins put human thermoregulation to shame. As the ambient temperature is lowered by a staggering 110 degrees, a penguin chick's core temperature changes by 1 degree. The level of sodium in your blood is tightly regulated between 135 and 145 milliequivalents per liter, a number controlled by exquisite sensors in the brain, coupled with an equally accurate mechanism that retains or dispenses salt and water in the kidneys. Cannon's insight inverted long-established logic. Physiologists for generations had described animals as assemblages of machines, as sums of dynamic parts. Muscles were motors, the heart a pump, the nerves were electrical conduits. Pulsing, swiveling, pumping, sparking, the emphasis was on movement, on action, on work. Don't just stand there, do something. In shifting physiology's focus from action to the maintenance of fixity, Cannon and Bernard had fundamentally changed our conception of how the human body works. A major point of physiological activity, paradoxically, was to enable stasis. Don't just do something, stand there. All around Cannon, theorists were thrilling to the idea of self-righting systems resistant to the buffeting forces of change. The English botanist Arthur Tansley coined the word ecosystem in 1935. The maintenance of stability would soon be described as one of the cardinal properties of ecologies. And soon economists were relating homeostasis to self-correcting markets. Norbert Wiener, the mathematician, saw that machines and creatures might be governed by autonomous control systems stabilized by feedback loops. Cells, cities, societies, even political institutions had the capacity to steady their states through the actions of self-regulated and counterpoised forces. And Lewis Carroll's Red Queen was their symbolic monarch. The world is spinning so fast under her feet, she tells Alice, that it takes all the running you can do to keep right in the same place. So this goes on a little bit. What was he like at rest and in motion? This is my father. He loved to travel nearly as much as my mother loathed to. In the early days of every summer while I was growing up, he would come home one evening with 4 tickets and a visa form and announce that we would be decamping in a fortnight or so to some unfamiliar foreign location: Cairo, Addis Ababa, Bangkok, pre-Glasnost, Moscow, post-Shah, Tehran, while my mother stewed privately about what to pack, whom to ask for advice, and what to feed her children during the trip. It's tempting to psychologize this. He was the boy who had been forced to flee his home, but sometimes, as he liked to point out, a ticket across a border is a ticket across a border. Oh, and he loved markets. Malls, particularly American ones, depressed him terminally. To shop without confrontation was to die without a battle. When signs reading fixed price began to appear in Delhi's shopping arcade, mainly to fend off bargain hounds like him, he saw it as a symbol of the impending end of civilization. But he never met a man with a pushcart whom he didn't give his heart to. Perhaps it was fated then that the first of his falls, more than a year earlier, occurred as he made his way back from the neighborhood market with a bag of onions in each hand. That the first responders were fruit and vegetable vendors who knew him by name and who knew exactly where he lived, and that they brought him home like slightly banged up royalty on a repurposed fruit cart. He told us that he had tripped on a loose stone, and for a while things seemed to settle at home. But the world had already begun to shift around him. His sense of balance worsened daily. My mother hired a physical therapist. A carpenter came to attach firm wooden rails to the bed that he'd always slept in. When I went to see him late that summer, it seemed as if a biblical punishment had rained down on him. The man who wanted to be constantly on the move was confined to his bed, his shoes confiscated, his cane hidden, so that he would not find it and be tempted to roam. One night when he was particularly delirious, we tied him to the bed railings with pajama strings to keep him from falling off. I woke up in the half-light of dawn and saw him crying softly into his bound hands and promised never to do that again. And then, quietly, a new kind of physiology began to coalesce around him. The fruit and vegetable sellers began to turn up at home. The daytime nurse, a scraggly young man named Vishnu, the god, among other things, of maintenance and preservation, made a habit of propping him up in his rocking chair on the balcony every morning and having the various vendors congregate below like a worshipful throng. My father was delighted to be back among the believers. He would banter with them from above, a king under house arrest, but a king nonetheless, berating them about their prices, protesting the abysmal quality of the eggplants, asking why he, at his age, must suffer the sins of their bruised cauliflowers, and why the fish was never quite fresh. It was a small miracle. Mr. Mukherjee could not go to the market, so the market came to Mr. Mukherjee. In retrospect, I understood that this too was a homeostasis of sorts. The little rituals saved him. They staved off another fall. They restored his dignity, his need for constancy. At death you break up, Philip Larkin wrote. The bits that were you start speeding away from each other forever with no one to see. But for a while, my experience of my father's dying was not his breaking up into cometary bits. It was the opposite, his being held together by an infinitude of minute forces. He knew he was losing the cosmic bargain, but the onion seller, at least, would still cut him a good deal. And then things fell apart in a Hemingway sort of way, gradually at first and then all at once. Bishnu had to go home to his village because his hepatitis had flared, and so a new attendant was recruited to replace him. The daily routine now devolved into chaos. One afternoon, when my father should have been safely positioned on the balcony, the attendant left him at home. Within a few minutes, my father had squirmed out of his chair, eased his feet into his slippers, and tottered his way to the kitchen. He touched my mother's right shoulder, a small gesture so familiar to her from his normal days that she neglected to turn around and question why he was standing in the kitchen beside her. By the time she'd spun around, he was beginning to tumble sideways. He hit his head on the richly veined marble countertop that he was so proud of. Calcutta, he would say, not Calcutta, to remind people how far he'd come in life, and then he landed with a dull thud on the floor. A blow to the brain is a good way to eject someone from the equilibrium of free and independent life. Of all organs, the brain, ironically, has the least room to expand. The skull is a fixed space. Elsewhere in the body, blood will eventually flow out, but blood in the skull can stay in like a festering secret, forming a clot and then pressing down on the neural tissue. The clot can grow, further increasing the pressure and progressively crippling brain function in a cascading process beyond the reach of homeostasis. Indeed, once self-regulation fails, complex systems of all kinds can be claimed by a version of this process, sometimes called a failure cascade. A storm-battered tree takes down a transmission line. The increased load causes another network to fail, further increasing the load, turning a local outage into a regional blackout. Such is the power of homeostasis that it's hard to see such a failure cascade coming. Everything returns to normal until normality itself gives way. About 2 hours after his fall in the kitchen, my father seemed fine, except for a bruise that had ripened on his forehead. He asked for some water and then sat in his chair, glowering about his disrupted morning. The vendors had left. About 4 hours in, he said he felt uncomfortable. His neurons under pressure were sending him mixed messages. He was warm 1 minute and cold the next. He stripped his shirt off, sweating profusely. Then he wanted a blanket. He ate lunch like a southern Goldilocks. The chapatis were too hot, the dal was not spicy enough, and then he was overwhelmed with the need to sleep. He woke up an hour later, his arms flailing, his delirious, and my mother phoned me soon after. The speed of his unraveling was breathtaking. In that ICU ward, his sodium dropped precipitously, 131, 128, 122. His coma deepened from the imbalance of salts, and then his breathing dulled from the coma. Carbon dioxide and acid, when mixed with water, accumulated in his blood. His heart began to behave bizarrely, the muscles sluggish, the rhythms erratic, from the strange cocktail of acids, bases, and salts circulating in his blood. And then his kidneys began to fail. And because his kidneys were failing, his brain function worsened and thereby refueled the cycle of decay. But he wouldn't just accept death, he had to be bargained into it. His body fitfully rallied, hanging on to the final constancies of life with a kind of primordial cunning, as if my father knew down in his blood and in his bones that sometimes the market turns against you, that sometimes you must settle for the best among bad deals, and that a miserable equilibrium is still an equilibrium. A sodium of 125, he would take it, but with some cross-subsidy. He would shut down sectors of his brain as long as he could keep his heart. So that's this section on homeostasis. And then maybe I thought I would read finally from the gene, so we have more time. What time are we finishing, Olga? 5. Oh, okay. We have plenty of time. Okay. And maybe I'll come back to this idea of seed and soil. So this is from the last section of the gene. And here I was trying to get to the idea of a sense of the future. I had just read in preprints, actually the articles are still in preprints. I just read in preprints 2 attempts at describing very complicated human features by through genetic variants alone. Actually, I have a picture of one of them. It's in the middle of the talk, but I'm happy to show it to you, which shook me a little bit. And that was to solve the missing heritability of height. As many of you know, human height is extraordinarily heritable. It's one of the most heritable features that we know. Tall parents tend to have tall children. Shorter parents tend to have shorter children. But previous attempts to use various technologies to predict human height based on genetic variation had been relatively unsuccessful. So this idea that you could not really get to the variation of human height based on genetic variation, based on known genetic variation, was a challenge in the field. It was, many people have called it different names, but it was called the missing heritability of height. We knew it was heritable, but what the features, what the factors were that were contributing to height were unknown. And this remained the case for a long time until I read this paper. Actually, I was finishing my book, and I read this paper. It was then in preprint. It's still in some kind of preprint version. I'll come back to this. I think these are important. So this was basically the summary of it. It was from a computational physicist who started this work, and he went into a large biobank, now available publicly, the UK Biobank. And he used what he called a deep learning algorithm. I'm not a real expert, but what he did essentially, just to summarize it to a layperson, was that he tried to use an algorithmic way to fit on one axis the variation. So basically, imagine an enormous biobank. It, I think, now has 500,000 humans. And you have, very abstractly speaking, you have their genetic variations on one edge of the biobank or one line in the biobank, each of these individuals across the entire genome, and you have their actual height as another point. And the question is, can an algorithm attach connection weights to each of these enormous set of variations so that the algorithm can predict what the actual height is going to be based on genetic information alone? No information about the parents, just based on genetic information alone. And this was one attempt. It's apparently been refined since then, and you can see that it doesn't perform. This is the predicted height. This is the actual height. It doesn't perform exactly accurately, but it was already, to me, it was already rather shocking, because the fact that you could potentially, based on genetic information alone, predict the height of your unborn child begins to say something about a new universe that we might enter in. Because, of course, the things that I was interested in was not height. I was interested in breast cancer risk. But the investigators told me what they were working on, extremely complex genetic architecture, nearly 3,000 to 5,000 genes involved in just the prediction of height. I think this might have been refined since that time. But this is what they were working on. They were working on complex inheritable cancers, so very much what I'm interested in our field. Going back, just to give you a sense, this is the kind of genetics that we grew up with. This is BRCA1. This is the pedigree for BRCA1. But anyone who's really been a cancer physician or a cancer researcher knows that there are many, many, many women and men who have histories of breast cancers in their families, who are obviously cannot be ascribed to just BRCA1, BRCA2, or even some of the other genes that have been discovered since then, single gene mutations. So in fact, that's the majority of women with familial breast cancer. I think the numbers are not something like 70% of women with familial breast cancer cannot be described as having mutations in one of the 6 or 7 genes that confer single gene risk. And in the vocabulary of breast cancer, there was a word that came up called BRCA3. Some of you may have heard of this. BRCA3 was the word used to describe these women. It was like an unknown risk. It was like not having a gene, but knowing that you had the syndrome, not having a genetic annotation, but knowing that you were at risk because of familial disease. So the idea was that they were going after complex inheritable cancers so that we might be able to actually assign risk to a person based on their genetic information. But then, what else were they doing? I said, what else are you interested in? Diseases, as I said, but they were interested in IQ, whatever that might be, we can talk about it, skin color, bone density, mental illness, et cetera, et cetera, et cetera, et cetera, et cetera. And the idea was that although the heritability of many things, of many of these, begins to drop, it's not as clear as height, that if they could get somewhere that they could continue to refine this analysis with more and more, with larger and larger data sets to begin to approximate the heritability of some of these syndromes. So I don't need to tell this audience that this is a very, very destabilizing idea, at least it was for me, being able to predict complex features of our children based on genomic and genetic information. Even understanding that the environment can play an important role in all of this, leaving aside that question, is fundamentally destabilizing. So I'll read it from the end of the gene. This is from the last section, and it goes back to where the gene begins, which is the history of my mental illness in my family, schizophrenia and bipolar disorder. So we're coming back, to set the scene, we're coming back from a visit to my cousin, who's my paternal cousin, who's in a mental institution, permanently confined because he has no other services. He's lost all services. On the way back from Moni's institution in Calcutta, my father wanted to stop again outside the house where he had grown up, the place where they had brought his brother, this is my uncle, back in the throes of his mania. We drove in silence. We left the car at the narrow inlet of Hayat Khan Lane and walked into the cul-de-sac on foot. It was about 6 in the evening. The houses were lit by an oblique smoky light, and the air threatened rain. Bengalis have only one event in their history, partition, my father said. He was looking up at the balconies jutting above us and trying to recall the names of his former neighbors. A gentle drizzle began to descend on us, or perhaps it was just the drippings from the laundry, hanging thickly on clotheslines tacked across the houses. Partition was the defining event for every man and woman in this city. Either you lost your own home, or your home became a shelter for someone else. He pointed to the colonnades of windows above our head. Every family here had another family living within it. There were households within households, rooms inside rooms. When we arrived here, with our 4 steel trunks and our few salvaged possessions, we thought we were beginning a new world. We had experienced a catastrophe, but it was also a fresh start. Every house on that street, I knew, had its own story of steel trunks and salvaged possessions. It was as if all the inhabitants had been equalized, like a garden cut back to the roots in the winter. For a cohort of men and women, including my father, the journey from East to West Bengal, therefore, involved a radical resetting of all clocks. Thus began year 0. Time was splintered into 2 halves, the era before the cataclysm and the era after, BP and AP. This vivisection of history, the partition of partition, produced a strangely dissonant experience. The men and women of my father's generation perceived themselves as unwitting participants in a natural experiment. Once the clocks had been reset to 0, it was as if you could watch the lives, fates, and choices of human beings played out from some starting gate or from the beginning of time, from the beginning of artificial time. My father had experienced this experiment all too acutely. One brother had devolved into mania and depression. Another's sense of reality had splintered. What force or mechanism might explain such widely divergent fates and choices of individual human beings? In the 18th century, an individual's destiny was commonly described as a series of events ordained by God. Hindus had long believed that a person's fate was derived with nearly arithmetic precision by some calculus of the good and evil acts that he had performed in a previous life. God, in this scheme, was a glorified moral tax accountant, tallying and divvying portions of good and bad fate based on past investments and losses. The Christian God, capable of inexplicable compassion and equally inexplicable wrath, was a more mercurial bookkeeper, but he too was the ultimate, if more inscrutable, arbiter of destiny. 19th and 20th century medicine offered a more secular conception of fate and choice. Illness, perhaps the most concrete and universal acts of all acts of fate, could now be described in mechanistic and pathological terms, not as the arbitrary visitation of divine vengeance, but as the consequence of risks, exposures, predispositions, conditions, and behaviors. Choice was understood as an expression of an individual's psychology, but also of experiences, memories, traumas, and accumulated personal history. By the mid-20th century, identity, affinity, temperament, and preference, straightness versus gayness, or impulsivity versus caution, were increasingly described, therefore, as phenomena caused by the intersections of psychological impulses, personal histories, with some element of random choice. In other words, an epidemiology of destiny and choice was being born. In the early decades of the 21st century, we're learning to speak yet another language of cause and effect. We're beginning to describe illness, identity, affinity, temperament, preferences, and ultimately fate and choice in terms of genes and genomes. This is not to make the absurd claims that genes are the only lenses through which fundamental aspects of our nature and destiny can be viewed, but it is to propose and give serious consideration to one of the most provocative ideas about our history and future, that the influence of genes and gene networks on our lives and beings is richer, deeper, and ultimately more unnerving than we had previously imagined. This idea becomes even more provocative as we learn to interpret, alter, and ultimately manipulate our genes intentionally, thereby acquiring the ability to alter future fates and choices. Nature may, after all, be entirely approachable, Thomas Morgan wrote in 1919. He continued, her much advertised inscrutability has once more been found to be an illusion. I've often thought about the possible trajectories of my cousins and uncles' lives if they had been born in the future, say 50 or 100 years from now. Would our knowledge of their inherited vulnerabilities be used to find cures for the illnesses that had devastated their lives? Would that knowledge be used to normalize them? And if so, what moral, social, and biological hazards would that entail? Would such forms of knowledge enable new kinds of empathy and understanding, a new medicine? Or would they also nucleate novel forms of discrimination? Would the knowledge be used to define, ultimately, what is natural? But what is natural? On one hand, variation, mutation, change, inconstancy, divisibility, and flux. And on the other hand, constancy, permanence, indivisibility, fidelity. It should hardly surprise us that DNA, a molecule of contradictions, this is a quote, encodes an organism of contradictions. We seek constancy in heredity and find its opposite, variation. Mutants are necessary to maintain the essence of ourselves. Our genome has negotiated a fragile balance between counterpoised forces, pairing strand with opposite strand, mixing past and future, pitting memory against desire. It is the most human, definitionally, of all things that we possess. Its stewardship may therefore be the ultimate test of knowledge and of discrimination for our species. So I'll stop there. And we'll have questions. Hi, Paul. Did you clap? Did you clap? That was the condition.
Members of your family had schizophrenia, or they didn't have schizophrenia.
Correct.
I wonder what your thinking is about these results which have come out. After spending hundreds of millions of dollars, what they've come up with is 1,000 genes, each of which give you a 1 or 2% increase in the probability of getting it. And yet you don't see a scaling of that. You either get it or you don't. How can you explain, or do you have any thoughts about how the people who spend all that money can explain those results?
Well, I think they're really, let's take a step back. The step back that I think is important is, I'm not a neurologist or a psychiatrist, but I follow the field closely because of my own family history. To take a step back, I think it's quite clear that some variants are highly heritable. We know that from twin studies. We also know that from family histories. And in fact, that the latest, there was a study just concluded 2 months ago, where the heritability for some of the severest forms of schizophrenia was up to 80, 85%. So with numbers like that, if we had a large enough cohort, I suspect, much like these very highly heritable features, that we would in fact find the genes that were responsible. And my suspicion is that it would still be on the order of 1,000, 2,000, 3,000 genes. It would not surprise me that our older genetic methods will fail, that we have to find more powerful genetic methods, and some of those powerful genetic methods will go along these lines, in which we will have to teach algorithms to attach connection weights, as it were, to a massive range of human variation. And the sad story there will be, if you end up with 5,000 genes, how do you create a biologically plausible pathway, potentially, for medicine? If you're lucky, you might be able to, so in other words, if it's really for a single patient, death by 1,000 cuts, 5,000 cuts, and each of them is contributing small amounts of risk. Is everyone understanding what I'm saying, by the way? Yeah. Each of them is contributing a small amount of risk, much like in height. Then I wonder if our capacity to think about medical intervention for these people will be thwarted, because we can't organize that information into plausible pathways and deliver medicines. Now, I'm not a pessimist about this. I just think that we need to think about these things as we are throwing around terms like personalized medicine for psychiatry. We have to be cautious and think about, what if it turned out to be that most complex illness, not just mental illness, most complex illness fell in this spectrum in which small risks accumulated across the genome, each contributing small risk, ultimately adds up to the phenotype of illness. And we cannot compute or understand plausible interventional biological pathways to understand this further. I suspect that that's where we're going to end up going. I'll give you one last example, Paul, which is relevant, because we know this a little bit for cardiovascular disease. So if you look at people, there's a nice study out recently, if you look at people who have, young people who are at high risk for myocardial infarction, of 100 such people, 2 can be explained by 1 to 2 genetic gene variants. So those are people who have familial hypercholesterolemia or some other, PCSK9 alterations. 98 of those people who have MIs at a young age lie in this, what I would call the BRCA3 category of heart disease, in which they have, in that case, 300 to 500, maybe 1,000 genes contributing small amounts of risk, which add up to their actual risk. So the question then becomes, what do we do about that? And I've been thinking about that question. So what could we do about that? We could identify and quantify the risk. And then we have 3 kinds of choices, I think, all of which have caveats. We could, if we could do embryo selection. All sorts of moral hazards raised by that, if there were few enough. So for instance, if we knew the 5,000 odd genes gene variants that were contributing to schizophrenia risk, and if we had a baby which had all 5,000 of those, and we could quantify, based on what we knew, the risk of them developing schizophrenia at what number? I don't know what number. I mean, this is my own family's history. Maybe I have them. We could choose to not have that child. We could choose to find an actionable target, but that might be tough. It might defy our capacity to do so if you have to. If there was one dominant target, we, in some fantastical world, could crisp it out. Not so easy. But aside from this, I'm not sure what else to do. If anyone has any thoughts, I'd love them.
So you have no explanation then for the fact that there's large numbers of genes, each contributing 1% to the probability you'll get the disease, and yet it's an all or nothing disease.
Well, I don't think, I mean, in other words, in medicine, there are, I don't think that defies logic, does it? I mean, in other words, the ultimate phenotype of a disease, of course, is, there's an environmental interaction, which I'm putting aside for a second, but the ultimate development of a disease, of a full-blown disease, is demarcated by a physician. That's because they're drawing a line somewhere. They're saying, you have subpsychotic illness, you don't have, had one psychotic episode, never again, you're not schizophrenic, you had 17, you are. Most people, I suspect, lie in spectra of this. We know this from family histories. The definition of a disease as an all or nothing phenomenon is a human definition, particularly with mental illness. So that doesn't surprise me that you can accumulate small amounts of risk and be tipped over ultimately towards having a disease or not. It's not surprising to me in terms of physiology, and I certainly know it would not be surprising to anyone working in cancer. It's very common, actually. Other questions?
That was a great talk and a wonderful reading.
Thanks.
Thank you so much for coming to visit with us. What are your thoughts, sort of dovetailing off of this, on people who are normal and healthy getting their genome sequenced through 23andMe? And what are your thoughts in terms of what that's going to look like in the future?
Well, so my thoughts about this are that it's far too early to have any real substantive thing to say about your own genome sequenced through a commercial entity. You will certainly, which we will. The things that will find are mutations generally, mutations in highly penetrant genes which cause disease through a single genetic lesion. So BRCA1, BRCA2, cystic fibrosis genes, Huntington's genes, et cetera, you'll find those APO, familial hypercholesterolemia, the things that we've all learned are classical genetic understanding, medical genetic understanding on. I have to say that it should be a matter of some embarrassment and shame for us that despite having all this funding in this country, the first countries to mount a public genome project was the UK. And in fact, the riches of that project, with all their complications, some of which I showed you, are already emerging. I think by the time you get to 500,000, a million, 2 million, 4 million, 6 million genomes, all of which have been cross-annotated with whatever feature you're interested in, breast cancer risk, prostate cancer risk, other kinds of risk factors for diseases. I'm interested in cancer, that's why I keep saying cancer, but you might be interested in something else. That's when you start getting an enormous amount of depth of understanding, and I suspect, given the nature of the information, 20,000 odd genes, plus all the intergenic variants, introns, et cetera, you probably need on the order of several million before you can start getting at fundamental questions of risk. But I think technologically we could get there. 4 million genomes doesn't lie outside. 5 million genomes doesn't lie outside the capacity of sequencing ability or storage of information now. Those were upper limits in the past, but that's not the case now. What kind of world that will augur is a totally separate question. And this, actually, I don't know if you know this, but so Ken Burns is also doing The Gene as a film, and we've actually already started shooting, doing interviews for it. They were at the Rockefeller maybe 9 months ago. And that's one of the questions that echoes through the film, because this is where we're edging up to. So the last section is questions like you're asking, Paul, questions like you're asking. Okay, sorry. There were more questions.
I have two very disparate questions, but since I have the mic, I'll ask them
You
together.
can ask them both. Yeah. I'm going to drink some water.
The first question is trying to reconcile your first part of the talk when you talked about the involvement of environment, both micro and macro environment.
Yeah.
And your final part of the talk, which really focused on the intrinsic natures of multiple, but genes which are all contained, which are cell intrinsic,
Yeah.
which determine largely everything in some studies. So how do you reconcile the influence that the environment plays in with the genes that seems to be having such a preponderant effect?
So just to be very clear, it is far from obvious to me. The 2 points that you're making are far from obvious to me, and we should be clear about them. The gene variants that set up risk for disease may not be, and in fact are often not going to be, cell autonomous. We know this again from cancer risk. They may in fact be genes that are microenvironmental. We know this actually from multiple studies. So just to be clear about that. So just because they're genes doesn't mean that they're autonomous to the cell that's causing pathology. They may be in the stromal cell. They may be in the gene variant, maybe an immune gene variant, et cetera. But yes, keep going now.
To some extent, it seems to be independent of the environment.
The macro environment.
The
yes.
macro environment.
Yeah.
So that was the first question. And then the second question is talking about homeostasis and the fact that if you start looking at an organism and its pathology, trying to pull it southwards and kind of irredeemable to some extent. But that is not true in majority of the cases. Majority of the diseases we can cure.
Really?
The flu, for example, we don't have to do much, but the body is able to fix itself, right? Most of us get, most of the diseases that we will have in our lifetime, I think our body is able to fix it either with some nudging or without. The ones
Really?
they cannot will accumulate and lead it southwards. But what I'm trying to say is, it's probably not always true that that all the pathology is permanent and going to drag it.
I think you're right. I mean, there's certainly no claim here that all pathology is permanent. Actually, what's interesting is, if I don't have this in this slide, there's actually a nice, one piece of information that you might like to know is the curve of all-cause mortality in the United States, which looks like, actually, it's an interesting curve. It's interesting because we are in 2018, which is exactly 100 years from 1918, which, of course, was the Spanish flu. So if you look at the curve of pathology, of mortality in the United States, it starts off in the 1900s, slowly goes downwards. There's a peak in 1918, then drops down again, continues to drop downwards, and finishes downwards. That's understandable. What's interesting is if you split that curve into two components, the so-called infectious and chronic causes of disease, which goes to your point about the flu, the infectious mortality in the United States entirely parallels the total mortality. So it looks like this. It comes down, peaks up in 1918, drops down again, and continues to fall. What does the curve of, therefore, what must the curve of non-infectious mortality in the United States across 118 years look like? Any guesses? It's a completely flat line. From 1900 to 2018, if you plot with everything we've done, it's not totally flat. You have to look at it with a microscope, and there's a little dip towards the end of about 5, 6 years. But it's an astonishing split. If I have time, I'll show it to you. I actually have a plot of it somewhere. If I have time, I can show it to you. Actually, it's worth seeing because it's so enlightening. Sorry, keep talking. I'll show it to you. Except my computer's not working.
To
You didn't answer my first question.
Well, the first question has two parts to it. One is that the microenvironmental variation will be captured in genetic risk. Macroenvironmental variation is you're absolutely right, it's a completely different universe, and we know very little about it, I think. For some diseases, like cardiovascular disease, we know a little bit more. For other diseases, we know very little. So I think it's not going to be captured. This is just for fun.
model in many ways, and he asked 2 questions, so I think
So you
I
don't
will
ask 2
too.
questions as well.
So my other question, after we go through this curve, you had mentioned this older
This
model.
is what it is. So total mortality, infectious mortality, non-infectious mortality. Okay.
So you had mentioned this model of, thinking about a gene and its specific product, and if we target that product, then we can cure disease. And you mentioned that you have restructured your laboratory around different paradigms. I was wondering if you could tell us a little bit about the new paradigms that you're thinking of in research and how you've restructured your work around those paradigms.
So some of it is still in process, and some of it has been very unsuccessful. So, but I'll tell you what the principles are. The principles are that if a project does not have one step away from human utility, we don't do them. The second principle is that the outlet for the outlet for every project should be a human clinical trial, or and take this as you will, or a company that supports a human clinical trial. So basically an entrepreneurial outlet. And if it's not that, if it's not easily perceivable in 1 to 2 steps, we won't do the work. The people who come to train in the laboratory, I generally tell them that I'm not very good, I think, at training them to be PIs in academic settings. I can train them to be physician scientists to go back to the clinic. But if they're seeking, I can train them to lead entrepreneurial roles, to bring medicines to human beings. I can train them to run clinical trials, but I'm unlikely to be able to train them to be PIs. The granting system of the laboratory has moved from more NIH or R01 funded to more and more funded through things that I couldn't previously had a very hard time dealing with, but organizations that support very project-focused research. And I can go on and on and on and on. It is anathema to academic practice, but I could only do it once I had tenure, basically. But it's totally anathema to academic practice. And in fact, we have said that we have split, to some extent, our priorities so that on the rare circumstance that we have, I think, a high-impact finding, which has relevance to human physiology because of the predispositions, we will publish in fancy journals, but we won't grovel at trying to publish in Cell and Nature. We published before there. We won't grovel and go through the groveling process that occurs in publishing in fancy journals, because if the research is not impactful, we'll know it up front and we'll just won't do it. And rather, we will publish papers in preprint, if possible. We will open it to the community to criticize. We will open it to replication. We'll actually often publish replicated results. And as I said, it's anathema to academic practice. If I had started this 7 years ago, there's no chance that I would be at the university that I'm in. So that's something I can talk to you more and more about it. And we've said also that the successful outlet for a scientific experiment should be a human trial.
Thank you. You talked very movingly about the end of life.
Thank you.
At the beginning of life, I think we're doing better than we did 80 years ago. The end of life, I'm not so sure. What do you think?
You know, I think it's not. I think it's not as bad as we make it out to be. Actually, if you look at real numbers, the United States is actually doesn't do badly with hospice care, for instance. Our goals are sometimes not aligned. We fight for a little bit longer than we would normally fight for, but our goals are. But I think that we, as a country, have become more thoughtful about end-of-life care, about hospice, about terminating medical intervention. In fact, the numbers reflect that. There's a little bit of a misperception. Hospice costs more in this country than it costs in other places. It often happens later than it happens in other places, but the use of hospice, the use of palliative care, the use of end-of-life care is not as bad as you would imagine. In fact, it lies in line with several European countries. Some European countries are outliers in that, but it lies in line with them. Those are my thoughts about it. Yes?
Hi, I second the idea that the way that you talked about homeostasis was very moving, so thank you. And the discussion made me think also about chronic illness and disability, where you have homeostasis maintained at a different level than you do in like a healthy person. And I'm wondering, do you think that it's valuable to consider how those homeostases are reestablished in chronic illnesses?
I think it's very valuable. I think those physiologies are very unknown to us. I think often in medicine we project our understanding of normal physiology into abnormal physiology. In other words, we make a conceptual leap and say, oh, you know, in pathology, it must be the case that everything else remains the same. But the only thing that's altered in this is, as I said, this is a very reductionist, gene-focused approach, and is correct. So if you look at, just to give you one example, if you look at CML, chronic myelogenous leukemia, if you look at the pathology of people with CML, if you look at the bone marrow of people with CML, in fact, the bone marrow is restored basically close to normalcy once they're on appropriate medicine, once they're on targeted therapy. And this gave us some confidence that, oh, you know, there's a switch, so you toggle the switch in one direction, a person goes into pathology, you give them a medicine, they toggle the switch off in the other direction, it gets restored. But we're finding out more and more that that's not the case with many other cancers, that there are a series of effects that underlie the ultimate development of the syndrome of a disease. Just to give you some examples, I mean, there are people here from the immunology world. Obviously, one of the first examples would be that we now know, which we didn't suspect to the extent we do, about the nature of the tumor microenvironment that has to obtain in order for a tumor to resist and to grow in the context of an immune system. So there's fundamental features of immune dysfunction locally, which we didn't know about. We knew about scientifically, but it's become quite clear in human studies as well, more and more clear in human studies. So you're absolutely right. I think imagining disease as, you know, here's a human being and a pathological switch is toggled, and, you know, and that if we retoggle that pathological switch, we would shut it off and restore balance, I think is simplistic. I think many such mechanisms often are pushed to the tipping point and break, ultimately leading to disease, and switching one of these back to normal often won't reset the whole disease. And I can give you very particular examples of such things. Yeah. Yes?
Hi. Any chance you could share a little bit about your writing career? Hi, Raphael here. Any chance you could share a little bit about your writing career, how you came to write the books that you ended up writing? Did you write before you wrote The Emperor of All Maladies? What type of writing had you been doing? How do you structure your sort of writing process? Do you start in outline mode, et cetera?
I had written a little bit before, but obviously nothing of the ambition of The Emperor. I wrote it. I wrote the first book as a fellow, and I think the secret for me there was to tell no one. I just did not tell anyone, because there were the world is full of inhibitory synapses. Virtually all the synapses are inhibitory. So, one way of moving forward, that is also not to be secretive about it, but just to move forward. And it helped that I could bring some freshness to the equation. That's actually, I tend to like to write like that, rather than writing like an expert and saying I know everything. It's obvious it's not true, but is to start and discover the process anew. It actually animates the right kind of writing, I think. And what's my process now like? So I've written a little bit. Didn't write for about 6 years when I worked on The Emperor. Then again went into, I had a kind of I was unable to produce some things for a while. Then went back to starting to write The Gene. Actually finished the film with Ken. Went back to writing The Gene. And then have now finally decided I'm going to write. So the books were meant to be a trilogy, and the third is a history of immunology. And the reason is that I began to understand that it's probably one of the first cellular systems or organ systems that we've learned to engineer. And we're coming up to a time that, if you imagine a vaccine as an attempt to engineer a cellular system, which it is, it would be one of the first cellular systems that we've learned to engineer, very much like the gene is one of the first biological informational systems we've learned to engineer. So there's some analogies that drive this kind of process. What else can I tell you? It's my writing process is a little bit frazzled. I mean, I sort of go back to something, abandon it, come back. I don't have a very linear way of doing things. I'm terrible with deadlines. What else do you want to know? Those are some things. Yes?
So my question is also about your process of writing.
Sorry, just wait for the microphone because people won't be able to hear you in the back. Oh, you can have mine.
Thank you. My question is also about your process of telling a story.
Yep.
So I'm curious about what drove you to choose writing, and now that you're dabbling in film, I'm curious about when you compare those processes for you. Of course, now that you're working with film, you have the backbone already prepared, and much of the creative processes happen. But they are definitely very different media to be able to tell stories and reach different audiences and reach the same audience in different ways. And I'm curious about, in the context of science and medicine, how effective each has been for you, and sort of your experience of knowing how to pick the appropriate vignettes and the appropriate narratives.
Well, so I'm not a filmmaker by any stretch of the imagination, but I like to collaborate very heavily. Ken and I had a very successful collaboration around cancer, I think. At least we both came out of it very energized. So the filmmaking aspects are very much his. On the other hand, the scripting was done for Emperor was done by an extraordinary group of scripters, including Jeffrey Ward and David Blistein and Barrack Goodman, who really took up all the heavy work of scripting. I worked quite closely with them. I worked very closely with Barrack and Jeffrey, and what the typical process of working would be that they would bring something. We had probably 80 viewings during the process of making, maybe 90 viewings, and we would sit down and sort of move things around. And everyone had a kind of role to play. My role was what I called, I was the human minder, which is to remind people that it was a principle by which Emperor and Gene was written. No 5 pages should go by without a real human story, which goes back to my lab. And so I was a human minder. I would tell them, no, 5 minutes has gone by. We need to go back to someone's life. it could be a scientist's life, it could be a doctor's life, but it had to be someone's life. It couldn't be some abstraction in space. Jeffrey Ward, who's a great writer, he wrote Vietnam most recently. He's an astonishing writer, wrote the Roosevelts. Jeffrey was as he calls it, he was the creator of stupid sentences. Because in the film world, and also when you write, at some point of time, someone has to say a stupid sentence, which goes something like, and therefore we learn, right? But you have to be able to say it in a way that's nuanced and interesting and powerful and thoughtful. But essentially what you're saying is, and from this we learned that, or here is where we are. It is now 1962, and we are in Boston, right? You have to be able to convey that, because otherwise it becomes too fancy. And everyone gets confused. So everyone had roles. Barack's a consummate filmmaker. Ken's really a consummate filmmaker, but also a very, very, very good editor. So he would cut. So anyway, those were the processes. Do we have time for one last question, and then we can talk? Sorry, last two questions, then we can stop. Yes?
So, related to that end-of-life question.
Yeah.
So, I hope you still remember that I rotated at Mass General with you under your supervision when I was a medical student in Japan.
So sorry.
So that was 14 years ago.
Sorry for you. I feel badly for you.
Yeah. Actually, so when I rotated with you, I told that I was kind of hesitant to be an oncologist. So when I rotated with you, I just lost my dad from the metastatic gastric cancer. And then, so at that time, so you try to convince me to be an oncologist and then to come to US, so to learn some integrated medicine, integrated both palliative care and then oncology.
Are you an oncologist now?
Yes,
See?
now I'm an oncologist. So
you owe me $20.
Then my question is, after your loss of your dad, so your recommendation is still valid? So
yes, I think so. As I said, I think, I'm not the only physician who's lost their father in human history. I think, but it was, to me, again, it was a reminder of things that I had thought about in medicine, but hadn't fully internalized or fully understood. People, some people, when they lose their parents, think about some things. I thought about homeostasis. One last question, sorry.
I'm curious how the sort of rise of your writing career has affected your life as a doctor. Not so much, in terms of the way you think conceptually, but just quite more literally in terms of, who you interact with, the patients you see, just your day-to-day life.
Yeah, it's affected quite badly, as you can imagine. One thing is that I had to bring down my clinic, seek out, which I did successfully, seek out partners that would take care of patients on the day-to-day basis, because I was actually failing to do that very well. Rather than doing that as a primary effort, I switched mostly, again, the principle that I like to think that working from principles is better than finding principles after you've done the work. So the idea that I had was that I should just run trials. I should be a PI on trials, and I should just run them and provide I would get personal gratification from that, and also be able to bring some skills that I think are, for me, better skills into the process. Virtually all of my clinic now focuses on trial running. Everyone's on trial. Everyone's on some kind of study. They range, but virtually everyone is on some kind of studies. And that's, if from that principle, actually, that strongly limits what I'm doing and what I won't do. So that's one way. I think we're done. I'm happy to hang around for a few minutes to answer questions or talk more. Thank you.